processes, once they exist, they need to go off and do stuff. But because you saw with the scheduler, they're not always in the CPU. When they're in the CPU executing, we'll call that the running state. And there's other states that we go through. And any operating system that uses a process model uses this process state transition, idealized model. Okay? Technically, by the way, this is a DFA that we're going to look at, but DFAs can be converted into NFAs, excuse me, and they can be converted into DFAs or what push-down automatas or whatever you want. We're just going to call it a state machine. How we would represent it on in a class like CS311, not something we're going to cover. There's a question over here? I saw a hand up. So, the idealized model, which all systems, Windows, Linux, Unix, XP6, at their core they have to have this model, because this is a requirement of the process model. We're using processes in this class. When a process enters the system, that is, it's fully initialized and ready to go, we put it in what's called the ready state, and sometimes called ready to run. In XP6, it's called runnable. So lots of different terms. Then remember that scheduler that we talked about? Its job, that figure out the next process to run, its job is to take some process in the ready state and assign it to the CPU. When you're assigned to the CPU, you're now in the running state. That's its job. That's the scheduler routine. After you've been running for a while, okay, the timer interrupt might go off and you get kicked out of the CPU. And we call that being descheduled. You could still run if only they would give you the CPU. You could do useful work. But they took the CPU away from you. The routine that actually kicks you out is called yield, and it calls the routine SCHED, I mentioned before, SCHED, that actually performs this transition. But you could also be doing I/O. Compared to the CPU, I/O fast or slow? Very slow. Okay, very, very slow. So when you're waiting on I/O, we don't want you being scheduled in the CPU, so we put you in a special state called blocked. Sometimes called sleeping. And in XP6 it's called sleeping. Okay, and then we term it sleeping on an event. Here we're saying we're blocked on I/O. This is the standard model. We'll see that the XP6 model down below changes these labels. When our I/O completes, or our event occurs, we can move back to ready, because now that that has completed, we could do useful work if we were given the CPU. So the scheduler routine only looks at ready processes in the ready state. That's its only job. Okay? It does not, the scheduler, spelled all the way out, does not take things out of the CPU. That's yield's job. Okay? But yield and sched are all part of the overall scheduling process. Okay? All of this is done by the scheduling process, including this. So all of this is scheduling a process. Okay, but the scheduler only does the top arc. So in XP6, what does that look like? What the process idealized model doesn't account for is, for the system that's using processes, how do we create a process? What does a process look like? What are its fields and its proc structure? How are they stored? Things like that. What happens when they call exit? Okay. So once we're running, we follow the state transition model. Notice that the idealized model does not talk about things like the proc structure. Okay. So in XP6, when we first boot the system, we have a fixed number of processes. Most systems create processes dynamically. XP6 does not, once again, in order to simplify the code so it's easier to understand. And we create them, and they're stored in what's called the unused state. Okay? Now, when we go to create a new process, we have to allocate one of those, but then we have to set the process up, all that ancillary information, and we have to load the code and all that kind of stuff before we can ever put it on the CPU. So it can't go directly from unused to ready or runnable. Instead, we put it in a special state called embryo. All operating systems do this. They give it a special state just so that nobody messes with it. Okay? Only the thread of control that's currently holding the embryo process and setting it up can actually modify it. Everyone else just goes, it's an embryo, I'm out of here. Okay? The scheduler will never see it. Once we finish initializing it, we'll transition it into the runnable state. And that makes the scheduler aware of it, and then it can be put into the CPU when the scheduler selects it. In order for a process to exit the system, even if you kill it, okay, even if you kill it, it has to be in the running state. So if you send it a kill and you say, I just terminated my process because it was waiting on I/O that will never happen, well, what happened, it was down there in the sleeping state. You sent it a kill signal. The operating system said, hey, process, you got a kill signal. You need to run that. And it goes, oh, wait, you're in the block state. Let's take you out of the block state, put you in the running state, because you can't detect that you've been killed until you're in the actual running state. Sorry, put you into runnable and then go to the running state. And then you'll notice that you're killed. You'll call exit, and you'll leave the system. When you leave the system, you're going to go to the state called zombie. And that's just that state we said before, where only the PID and the exit value are sitting around. And then the upper arc that says wait, that's where the parent process calls wait. Okay. So the wait arc is done in the parent process. Okay. Now, what happens if the parent doesn't call wait? Remember, we said that the very first process was a init. And init's job has a couple of jobs. Okay? And one of them is, if a parent exit, that is an interior node, goes away, it takes the subtree and graphs it up to a init at the top level. That is, it sets a init as the parent. So once a init is up and running, all it does is call wait forever. Okay? That's its job. We call, when the parent exits and there's still a child process around, we call those children orphans. And setting a init as their parent is called adopting the orphan. Okay, so you'll see those terms. We're trying to avoid using them anymore in computer science, but you will see them used quite a bit, especially by textbook authors that have been in the industry much longer. They're used to using that term. Now, remember how we said fork creates new processes? Remember how we said it creates new processes by cloning a process? Let's ask ourselves a question. Who creates the first process?
The bootloader.
There's no one to clone, so it can't be fork. So what happens is the first thing when the operating system starts up, in XV6, it will call a routine in proc.c called user init. User init's job is to set up the first process. That's all it does. Okay? And it does it manually. So it sets up everything up that cloning will do automatically for us later. That's set absolutely everything up. It's hard to read. Okay? I'm not going to force you to figure out the details of user init. You'll have to do some modifications to it in some of our future projects, but you won't change the initialization portion of it. You'll add to it, but you won't change it. It runs a init. And if we look at a init, which is init.c, it's a bunch of code about this long. Its job is to start the shell and then call wait. And that's all it does. Okay? Very simple program. So that's how it works. And that's how the entire model gets kicked off. So, remember that instruction pointer our processes have? The instruction pointer's job is to control the execution within the process, isn't it? It tells us which one to execute next. The call instruction modifies it, right? Jumps modify it, things like that. Okay? So it's the path through our code. So just think of that as like a drawing on your source code, right? This is where we go. That's called a thread. Okay? That path is called a thread. And at any particular point in time, the system registers have particular value that are unique to the thread. And we call that a thread context. Okay? Every process has at least one thread. With just if it only has one thread, we don't point out that it has one. So remember that we had a context in the process. Okay? It turns out that we need to have, for that path that we're going around, we're making function calls and all that. So each thread needs to be able to have its own stack frames and local variables and stuff. So each thread has to have its own stack. So a thread is identified by its thread context and its local stack. Everything else is shared with the process. So it's very lightweight to go from one thread to another. We just update the process's stack pointer and reload the registers in the CPU. Blindingly fast. Okay, on the order of about 12 milliseconds. Excuse me, nanoseconds. I'm old. I remember when milliseconds were fast. So, we share all this stuff. Okay? And threads, originally they were called threads of execution because this is the stack, this is the instruction pointer that we're tracking. Now we just call them threads. If we have multi-threading, that means we have multiple stacks and multiple contexts. XV6, as we saw, we looked at the process structure, is not multi-threaded. It's not that hard to make it, and a lot of schools do it. At the undergraduate level, I have you guys make it multi-threaded. If you want to do that, at the end of the term, I'll be happy to point you to some course at Columbia or someplace like that has that as an assignment. You can go ahead and do the assignment. It's not hard, but it's tricky. A lot of little finicky details. Okay. So the O-Step book has a bunch of things that they talk about. All right. When we said before that each process had that proc structure that we called a process control block, inside each process control block, if it has more than one thread, we create what are called thread control blocks. Okay. When there's only one, we merge the thread control block with the process control block and just call it a process control block. We don't put it as a substructure. So, if we make changes to local variables in a multi-threaded environment, we're only changing the thread's the local copy of it. They're on its own stack. But if we change things to the heap, the global data, then it's visible to all threads. Which is interesting because then we can use that memory in the heap to communicate between our threads, pass information back and forth. Okay. So, this is what a single-threaded process looks like. We have one thread of control, one code, one data, one set of files, one set of registers, one stack. Multi-threaded, they all share the same code, data, and files, and other ancillary information, but registers and stack are private to each thread. Now the reality is that each thread has access to every virtual address in the process space. So different threads could go and stomp all over some other thread. Okay. All right. So it's harder to program in a multi-threaded environment than a single-threaded environment because you have to be aware that there are other threads that are out there and there's specific programming techniques. If you take a class on multi-threaded programming, we'll talk to you about how to deal with that. We have some libraries provide some pretty good tools for doing that. Now, one of the things to note is a process is a schedulable entity. So if we have a single-threaded system where everything's a process model, whenever we do a context switch, we can only move the process in and out. Okay, we can only schedule the thread, which at this point is merged with the process. When we have multiple threads, it turns out the thread itself is the schedulable entity. So it turns out the individual threads of a process can be running on more than one CPU simultaneously. This is the way that threads dynamically adjust to what's called the CPU pool. If the operating system says, here, you can have 5 CPUs, and you've got 1,000 threads, you go like, fine, throw 5 of mine at it, And it says later, I'm going to give you 1,000 more. You go, hey, throw more threads at it. And then it says, I'm going to take some of those back. And it goes, oh, that sucks. I'm going to take some back. But it dynamically adjusts to a growing and shrinking number of CPUs, where a process cannot. Okay, the process, suddenly you get another CPU and you want to get some additional work done, you have to actually fork the process. Okay, and that's painful. All right, because duplicating all of this is a lot of copying of memory. Duplicating just this little bit is very small. Plus, individual processes cannot communicate to each other except through the wait call, unless you do very special programming techniques called shared memory. Okay, and that's an advanced programming technique, not something we're going to go into in this class, because it's pretty easy programming. Okay. So with multi-threading, the interesting thing is the threads can run in any order. If the top line says routine 1 runs before routine 2, then we run the final. Or we can do routine first. Or we can interleave them like we do on the third line. We'll see how to do that with scheduling, when we get scheduling algorithms. Or if in this case, in the last case, those last 2 lines, we have 2 processors, we can overlap them. So you see the first 3 all took the same amount of time. But as soon as we were able to do things in parallel, what we call concurrently, we're able to reduce the overall execution time working. And that is the principal benefit. One of the principal benefits of threads. Get more work done per unit of time. So we can use more CPUs. Okay? Now, we only got 1 minute left. We'll come back. We'll hit this final example when we come back. It's just the evolution of web servers. So it'll only take about 30 seconds. Questions? Thank you.
That's really